Good afternoon, fancy meat computers. How's everybody doing this fine afternoon? It's Wednesday. One week from today is our last class of the semester. Isn't that exciting? Isn't that exciting? You're just trying to make me say stuff for like an upcoming meme video, aren't you, Mark? Here's Nick! There. Is that a good clip? It's like, here's Johnny! So we got 3 people watching at the moment. Do you think we'll be able to break 8 today, or do you think, like, oh, please, I have much content to work with. I imagine you would. I imagine you would. I'm expecting, like a meme supercut that's, like, literally, like, at least 30 minutes of meme footage at this point. Like, you've been saving it all semester, man. Come on. That's okay. Doesn't have to be. You know, at a certain point, you're kind of like, you know, I think there's an actual like hard time restriction on the amount of time that a meme content video can take. You know. Oh, we've got 5 people watching. Aha. So how's Project 3 coming along, everyone? Is it going? I have noticed that there was sort of a flurry of questions about it last week, and then I haven't seen much in the way of questions about it since, so I assume you guys are working on other things this week. Please be aware, I'm going to say this once, because I'm going to have to say it 1,000 times, I cannot possibly give any extensions for Project 3. I can't. It's due the last day of classes. Mark hasn't started it yet. That's a bad sign. Yeah. Actually, I think I can do a better, more useful poll. So we got 6 people. All right. Well, not well. Haven't started. Or there's a Project 3? Question mark, exclamation mark? Okay. So we got 7 votes. So more people think it's going well than not well, so that's good. One person is a memer. I'm going to assume that if you selected there's a Project 3, then you are memeing, and you actually mean it's going well. Going to start it today since we had 2 assignments due yesterday. Yep, sounds about right. Well, you've got a week for it, you know? Which I don't mean to say procrastinate and leave it till next Tuesday. What I mean to say by that is, if you work on it a bit and you're having difficulty with it, you at least have some time to get answers to questions you might have about it before the thing's due. You know, I try to have a pretty good Piazza response rate for a guy who's like, you know, not a TA. Some of my TAs are pretty amazing. Ooh, 12 votes. We have 12 people watching. That's pretty amazing. Yeah. Well, at any rate. Oof. Yep. Godspeed, Aereo. Godspeed. So let's talk about topic or topic 14. We finished topic 13 last time. That was the topic on exceptions. I'm pretty sure. Yes, I remember showing you this this comic, so yes, we finished that. So that's why he puts comics at the end of the slides. Yeah, that's why I put comics at the ends of the slides, because I can remember if I've shown you a comic normally. Anyway, so we're going to talk about advanced topics in type theory. So this is like just finished awkward presentation for 3IO3 yesterday. I mean, couldn't you just say presentation for 3IO3? Do you really have to say awkward? Isn't that implied by the fact that it's 3IO3? So, personally, I'm kind of excited about this. Is the exam on December 13th? Yes. I'm kind of interested and excited about this this topic because it's kind of something outside of the usual sorts of lectures that I do, which are very, you know, go through the chapter type things. This is a survey lecture. So what we're going to do, essentially, is we're going to go through a few items of note in the later chapters in Pierce. So obviously we're not going to be doing anything in a sufficient amount of depth for us to, for example, be able to prove any properties of any of these type systems, and rare is the case where we will be discussing any formal semantics. The point of this is really just to give you kind of a flavor for the different sub-disciplines in type theory that exist out there, that, you know, what their advantages, disadvantages are, what becomes possible with them, as opposed to, you know, other type systems. What are the applications of these advanced type systems? Where do they fit in? What types of languages use them, and for what? So I'm hoping that this is a slightly more interesting series of lectures than the rest of the course has been, because it's kind of more at the level of, you know, now that we've had a sufficiently rigorous introduction to simple type theory, there are many, many different type theories that build off of simple type theory. And interestingly, many of them do so independently. So, like, once you know simple type theory, you can talk about recursive types in the absence of, like, subtyping or parametric polymorphism. But the three main ones that I'd like to cover with the remainder of this course are subtyping, recursive typing, and parametric polymorphism, or polymorphism in general. But yeah, I'd like to apologize for the fact that this set of slides is incomplete at the moment of creation. You can get a copy, a preliminary copy of the slides off of Avenue. I apologize. I haven't had time to proofread these just yet, so there are probably going to be a few spelling mistakes. I will try to constrain and restrain myself from fixing typos during the lecture, because that seems like a bad thing to do if it's not something like directly impacting a formula. But yeah, so we're going to talk about type theory. In theory, this might be the most valuable lecture in the course so far, but I don't know. Again, this is kind of a new thing for me, so I'm interested to see how it goes. Also, did I talk about course evaluations? If I didn't talk about course evaluations are up. Give me a course evaluation. If you give me enough if you hit 75% of the class giving me a course evaluation, I'll knock some marks, 2 marks off the denominator of Project 1, I think I said on the Avenue announcement. But fill out the course evaluation. So, advanced topics in type theory. So, you may have noticed during the last topic that our terms of study are beginning to require more advanced type formulations in order to work. So if you think back in the very recent past to error, right? Remember that the error type, the typing rule for error specified that error could have any type validly. This is not something that, technically speaking, exists in simple type theory. We discussed a couple of ways of addressing that issue during that lecture. One was using subtyping, and the other was using parametric polymorphism. Hopefully, by the end of this, you'll have a better idea of what those terms actually mean. So, the simple type theory we have discussed so far is fine insofar as it goes, but real-world languages require a bit more horsepower. Simple type theory it's really the, it's like we've laid in the foundation and the structure for an apartment building, and now we're putting in like the electrical and the plumbing. That's the way to think about it. Like most of all the type theories that we're going to be talking about are constructed on the back of simple type theory. So nothing that we have said about simple type theory is going to be invalidated by any of this. So, for our last lecture topic, we will survey extended topics in type theory. So, let's talk about subtyping. Introduction to subtyping. So, one of the advantages of simple type theory is that language extensions are orthogonal. That is to say, orthogonal in the geometric sense. X is orthogonal to Y, so you can go along X without impacting your Y position. Essentially, the semantics of each language feature functioned roughly independently of each other, except in certain cases, like sequencing and referencing, where you needed like a couple of previous additions to formalize another addition. Subtyping integrates our language semantics into a more cohesive whole. In terms of the Curry-Howard correspondence, subtyping is an extension of partial orders over types. So, if you all remember, way back in September, when we had our sort of mathematical preliminary lecture, we talked about posits, and we talked about what constitutes an ordering, what constitutes a total order, partial order, etc., etc. We never really used that, however, until now. So the idea is that you can have an ordering relation over the elements of the set of types, right? This allows you to construct a partially ordered set from the set of types, which can be useful. So, here is a motivating example. Sometimes, simple types are a bit stubborn. Who mixed their ord in my typeset? Exactly. Simple types can be a bit stubborn in that the things we should expect to work without much fuss are not actually correct constructions. So consider the following term. If we have a lambda abstracted record R, that record being typed X has type nat, and like no other things are specified in the record type, pardon me, and then we project X from R. If we apply to this function, which is basically just take some record and project X out of it, if we apply the record X is equal to 0, Y is equal to 1, this is not a well-typed term, right? Because the type of this term would be record type X is nat, Y is nat, right? but that's not the same thing as just x is nat. So this would be a type incompatibility. Under simple type theory, this is an invalid construct. This term is untypable, but the meaning is obvious, right? Clearly, the intention is that lambda picks out the x-labeled record entry using projection. Not only that, we could extend this to say this lambda function is intended to pick out the x-labeled record entry of any record that has an x label in it, right? That's sort of where we are going with this, right? So the idea is similar to how we use the underscore character in Haskell to denote a don't care value, right? We don't care about any of the other elements that we might be in the tuple that we're projecting x from, because we're really only interested in projecting x, right? All we really need for execution is a record, is that the record we are receiving has some field x. We don't care about the rest of the record, precisely. Not all types were created equal. The goal of typing, or the goal of subtyping, is to refine our typing rules so that they can accept terms like the one on the previous slide, which, you know, insofar as the record we would be applying to the lambda contains x, and that x is of the correct value, or, sorry, is of the correct type, there's no reason why that should be an invalid operation. In fact, that could be a very useful operation. So, we accomplish this by formalizing the intuition that some types are more informative than others. We can say that a type S could be a subtype of some other type T by writing S is a subtype of T. For those of you who are listening to the podcast version, this is the symbol we're using here is less than colon. So S less than colon T indicates S is a subtype of T. By this, we mean that any term S can be safely used where T is expected. This is called the principle of safe substitution. So, take, for example, some sets that everybody should be familiar with: the natural numbers, the integers, and the real numbers. So, it should be common knowledge, or at least very easily derivable for you, that the natural numbers are a strict subset of the integers, and the integers are a strict subset of the real numbers. Most controversial thing I've said, I know, right? Therefore, any element n is valid. Any element of n is valid in any situation calling for an element of the set of integers. I wanted to call it z. Can I call it z? I think I could call it z. An element of n is valid in any situation calling for an element of z, and either n or z are valid in contexts requiring r. Using subtyping, we would say that nat is a subtype of int, which is a subtype of real. Good. Any questions so far? Zebra. Yes. Zebra. I gotta rip that off for a meme. That sounds like a meme to me. So, this property is formalized in the property of subsumption, which is just a fun word. So, more intuitively, we take S being a subtype of T to mean that the set of values in S is a subset of the set of values in T. So, or conversely, T, so the values mapping to T as a type are a superset of those in S. We can try to force it into the 1MD3 exam. Sure. So it's important to note here that this is equivalent to subset equals, not strict subset, right? This is equivalent to subset equals. So S may contain the same number of values as T. It may contain the same values as T even, but it may contain no values that are not in T, and it does not need to contain all of the values that are in T. So this is formalized by the following subsumption rule. So if we have T being typed, so if we have, pardon me, if we have T being typed as some type S, and we have some type S being a subtype of T, that means that T is also well typed according to T. So this breaks some things. Crucially, it also breaks, it breaks the property that every term only has one type, right? Which is a very, important property in simply typed, in simple type theory. But, it turns out that in nature things can have multiple types. So this is actually a more close approximation of the underlying reality of life and existence. But anyway, so for our example from previously, we can now define the record type X has type nat, Y has type nat as a subtype of X has type nat. So the record type for X and Y can satisfy a type restraint, a type constraint requiring X having type natural. If you were wondering what ascription is useful for, this is what ascription is useful for. How about the reverse way? If a term is in type T, does that imply that that term is in type S? And the answer is no, it doesn't. So let's go back to the numbers, right? So let's take a term which is a valid natural number, say 7, right? 7, and I know you're not supposed to do proof by example, but proof during a lecture, this can help clarify intuitions. 7 is both a valid integer and a real number. -7 is not in the set of natural numbers, but it is in the set of integers and real numbers. And, -7.3 is only in the set of real numbers, right? So a term being a subtype, a term being an element of a particular subtype doesn't go up the chain, and that's kind of the crucial property. Otherwise, you'd be talking about type equivalency, right? You'd, yeah. Yes. Then we need to define the subtype rules. What do you mean? What do you mean the subtype rules? I'm confused by your statement. But yeah, the whole point of this is that it's unidirectional, right? Awesome. Cool. Yeah. I have to say, and I'm just handing out a compliment here. The people who are still in this class right now, probably the best students. Just gonna say. You're here, you're on time, you're actually watching concurrent. You guys are awesome. Let's just say the students currently watching are a subset of all the good students in the class. Let's put it that way. So, question. How is xy a subset of x? I would expect it to be the other way around. Yes. Okay, so John. So the thing you have to think to get this is think about it like it's inheritance, right? I think Nick's choice of operand is confusing. No. The bigger one is the subtype of the smaller one. This one is the subtype. This one is the type. This one's S. This one's T. X is the superset. Yes, that's what I'm saying. This is the superset. So, oh, like how we formalize, yeah, good. Cool, yeah. So, like we're going to talk a little bit about object-oriented because it turns out that subtyping is how classes are typed, right? The bigger is a subtype of the smaller, then int is a subtype of natural. No. So what's more specific? A one tuple or a two tuple? Right? So the way you should think about this is as levels of specificity. Yeah, I joke, of course. Any set containing X typed nat makes sense to be the super of X with other stuff. Yeah, it's a bad first example. Well, it's the one that the textbook used, you know. And I know it doesn't quite jive with the number example, but I really think the number example is like that's a primary example. I think that's a really good example to sort of put it in your brain. But yeah. So good. Okay, good. We're following along. This is good. So yeah, like it really is the property. Like if you think about it this way, right? Think about classes, right? If you have a base class and a derived class, any situation which calls for the base class can use the derived class, right? In object-oriented programming. So that's the same relation. And that's, as we're going to see, that's actually, that's related to subtyping. Like, subtyping is the way you formalize that relation. So we're talking about inheritance. But yeah. Just don't call it a subset. I mean, it's a subtype. Yeah, I should formalize. Yeah. This is a subtype of this type. There you go. Anyway. So, let's take a brief interlude and talk about Haskellian type classes. Giving the user access to subtyping directly is considered too impure for Haskell. Haskell relies on having a more simplified, more rigid type system, as most of its useful compiler errors are type errors. The principle of safe substitution would foul this up, and the benefits derived are marginal. Basically, Haskell creates this type of functionality in other ways. It doesn't need subtyping to be able to do this. Yes. Haskell has another way of performing the same functionality, which is type variables, right? So, type variables in Haskell. This is supposed to be a pun on I always get typecast. But anyway. Although I really should have saved that one for casting. Anyway. So consider the following. If we have a function head, it takes a list of A and produces an A. If we have a function equality, like the equality comparison, if you didn't know, in Haskell, that's how you define an infix operation. Like, You can define a function as being infix by putting it in parentheses, which is kind of cool. But so we have A to bool, and we also specify that A is a member of the type class EQ. The use of a lowercase letter indicates a type variable in Haskell. So head takes a list containing any type and separates out the head. The phrase EQA equals sign greater than, which is, I guess, double arrow, constrains the type variable A so that it is a member of the EQ type class. EQ is a supertype class with many subtype classes. So, type classes work similarly to subtypes. So this is not a complete diagram of all of these type classes in Haskell, but it's a reasonable proportion of them. There are a number of type classes in Haskell that don't have an ordering relationship to the rest of the diagram, like read and show. Show in particular is one that you probably will have run into before. But you know, these things define various properties. In order, like if a type is included in EQ, that means that it's equatable, and each one of these comes with a certain number of operations that you know, like if you define a type as being a member of EQ, that means you get equality comparison for it for free. Ordering, like putting it in ORD, allows it to be orderable, you know. And you can see we get more and more specific as we go down the diagram, eventually getting into fractional floating and real floats, or, you know, integrals from, you know. So, yeah. You know, numbers contain, like, everything past here. It's like integers, integrals, floating points, and doubles. Anyway, so the fractional type class, for example, contains all of the elements of real frac, floating, and real float. So it contains everything in here. Int and integer are members of integral and all supertype classes. Float and double are members of real float and of all supertype classes. So, yes. Like you could imagine, in Haskell, let's say you wanted to make a data type for jelly bean colors, right? And because you're a literal psychotic crazy person, you believe that there is there is meaning to ordering over colors. Well, I mean, I guess you don't have to be crazy to think that colors can be ordered, because you can order them according to spectrum, like spectral wavelengths. But yes, anyway. All right, I retract my statement. If you think that colors can be ordered, then you're not crazy. If you think it's useful to order them, that might be crazy. But yeah, anyway. So if you wanted to impose an ordering over something that wasn't a number, it would be a member of ORD, possibly also a member of EQ, but it would not be a member of any of the other type classes. In fact, if you made it a member of ORD, it would automatically be an EQ, right? Because each one of these is a superset of the thing it points to. Okay? So far, so good? So, let's talk about applications to object-oriented programming. Subtyping is a key feature of object-oriented programming. Color theory requires a strict ordering to the colors. It is a hierarchy, after all. Yeah, fine. In the context of jelly beans, though, and it doesn't make, like, if you're a person who arranges your M&Ms by color before eating them, it's like you're either doing it for fun, but if you're either doing it for fun or you're doing it compulsively, right? And if you're doing it compulsively, it's like that's a compulsion. Anyway, so applications to object-oriented programming. Different languages will define things in slightly different ways, of course. Object-oriented in C++ looks a little different from Java, which looks a little bit different from C#, and all of those look very different from Python, which sucks. Red jelly beans objectively taste better than the green. I don't fight anyone on the death to that. I don't disagree. Especially when they're mint. I think mint jelly beans are kind of weird, but anyway. So the following is a good general description, especially for the more rigorously typed languages, not Python. So, the type of an object is its interface. That is, it's the set of names and types of its operations, similar to our presentation of record types. Python should do some self-reflection. Excellent. Someone else has got to put a comment in, or else Mark has completely dominated the chat again. There we go. Thank you. So you have a class, right? You have a set of methods. Each one of those methods has a type signature, right? Because you have the types of the arguments, and you have the return type. That's a type signature. So you have a collection of type signatures that are all tagged with method names. That is an interface. That is the type of an object. Boom. Everybody knows that HSV is the best color space. So, an object's internal representation does not appear in its type because execution is not the purpose of type checking. So, for the purposes of type checking objects, we're not really interested in the implementation details of the object itself, so long as those implementation details themselves type check, right? So long as the object itself is correct. I see we have controversial opinions in the chat. That's okay. I'll drop my pencil. So long as the object has, as long as it type checks itself, as long as it's syntactically and type correct, we're not really concerned about the functionality because we're just concerned about the typing semantics, not the execution semantics. So, one of the most characteristic qualities of object-oriented is that objects of many shapes can be manipulated by the same client code. Anybody who's used object-oriented programming to any great degree will understand that this is a crucial feature. This is like the one thing that makes object-oriented work is you don't necessarily have to know the object. As long as it has this particular method, that method can be called. So, that is, we can call some method on any object whose class defines it. If the typing of our method is defined as follows, let's say m is some method from int to bool, and we have a class with an interface, some method int to bool, function x, function y, we can express the typing constraint as the interface is a subtype of the type of the method. So this is an interesting one, right? Because it's you have more supertypes than subtypes. You have one subtype that branches into multiple supertypes. And normally we like to flip that around and think of things as in a more strict hierarchy. We like to think of things hierarchically with small amounts at the top and big amounts at the bottom. Just because we're we're physical animals that are oriented by gravity, and it's harder to put things at the top of things than to have things at the bottom of things, which is why all of our diagrams are like bottom heavy and top light. But anyway, so in this case, we've got multiple supertypes with one big subtype at the bottom, which is something we can do because this is a partially ordered set, not a total ordered set. So, however, if we had some other type, some other class which defines the same method in a different way, so let's say instead of being int to bool, some method was int to a record containing 2 ints, then I prime would not be a subtype of M. Such usage would fail to type check. So you have to use your methods correctly, even if you've got the name right, essentially. So, object interfaces fit naturally into the subtype relation. If an object satisfies an interface I, then it clearly also satisfies any interface J, which lists fewer operations than I. Any context expecting the interface J wouldn't be bothered by the extra operations in I, in other words. This ability to ignore parts of an object's interface allows us to write a single piece of code that manipulates many different objects uniformly. In effect, we are declaring a set of operations common to many classes. So there you go. Any questions about that? Can I get a thumbs up at least? Anybody still paying attention? There we go. Thank you. Seems like the lag might be a bit long, or maybe I'm just hyped up on math. Maybe that's the problem. The teacher took math before class. It's like math or meth? Yes. All right, so we got 6 minutes left in class, which is enough time to sort of get briefly into recursive types. So why don't we get that underway? So, recursive types. Consider the humble list. Lists are one of a large family of common structures, including queues and trees, binary, labeled, and abstract syntax. These structures have a simple, regular structure, but may grow to unbounded size. Clearly, it doesn't make sense to add a new primitive type for every possible size of these data structures. You know, you don't have a separate type for, you know, a list containing 1 element, a list containing 2 elements, a list containing 3 elements, a list containing 4 elements, all the way to infinity. That wouldn't make that would make hardly any sense whatsoever. Which, by the way, incidentally, is exactly how we type tuples. So, if only there was some sort of way of defining data structures where an element can contain 1 or more copies of itself. Oh, if only there was some kind of mathematical construction that was highly related to the idea of induction that allowed us to define things using sub-definitions of itself. What's the word for it? What's the word for it? It's recursion, my friends. We can represent the fact that a list is either nil or a cons pair using tuples and variants as so. So if we have a list of naturals, that can have the variant type, and I know we kind of glossed over variant types, but basically it's one or the other. It can have the variant type nil or cons, where cons has a tuple type, it has a pair type, and nil just has type unit. The nil component needs no typing function, since the tag itself already tells us everything we need to know. For the cons component, the first element should be a nat, and the second element should be another natural list. Ta-da! We can think of this specification as an infinite tree. So, you have a list, it has nil, which is unit, and cons, which is a pair containing nat and another cons, or, another list, which, etc., etc., etc. You can unfold it off to infinity. With our last definition, we have a bit too much loaded in the name natlist, however. If we isolate the recursion on the left-hand side of the equation, then we can have fully anonymized recursive type equations. Yay! Fully anonymized recursive type equations! So if we take the following, which is our definition from 2 slides ago, and then we introduce the recursive type operator mu, recursive operator for types, mu, or mu, then we can say natlist is equal to mu x, nil is unit, cons is nat x, where x is a type variable. Using parametric polymorphism, we can also abstract out the nat, this guy here, to obtain a typing for general lists. Typing abstractions use the lambda, but type variables are capitalized. So we could even abstract this further to say lambda x mu y, nil still is unit, but cons is a pair between an x and a y. Ta-da. Any questions? We haven't talked about lambda yet. We'll be talking about it more once I write the slides on polymorphism. Let me get a thumbs up. I think the white jelly beans are the best. Cool. Does anybody have any questions? Any off-the-wall comments? What is mu again, please? It's a recursion operator. So essentially, all it does is it says this is a recursion variable. So what it does is it allows us to anonymize things, so we don't need this half. So, like, notice that the name natlist doesn't appear anywhere in here, right? So we could, in theory, just sort of bracket this bit off, deal with it separately in an equation, and, just use it by itself. Like, the question you have to ask yourself is, like, if you wanted to use a recursive type inside of a lambda abstraction, right? Say you wanted to put a recursive type inside of a type annotation inside of a lambda abstraction, right? How would you do that if you didn't have like a specific way of designating a recursion variable? And so they just use mu. I don't know why they used mu. Like, I was trying to figure out like why mu, and the best I could think of was like, I think mu is the Greek letter after lambda. I could be wrong about that, but let's take a look. Greek letters. Learn the Greek alphabet. There we go. It's, yeah, so mu is the letter after lambda, so I imagine that's why it's been used. Alpha, beta, gamma, delta, epsilon, zeta, eta, theta, iota, kappa, lambda, mu, nu, psi, omicron, pi, rho, sigma, tau, epsilon, phi, chi, psi, and omega. Omicron is just O. But let's see here. That's 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Wow. So we're on variant 15 now then. Good. Well, if nobody has any questions, then I'll give you guys a minute or two if you have any more questions, but if not, then I will be logging off here. As you can see, I have some work to do before Friday to get some more slides prepared, but you know, it is what it is. Okay, well, take her easy, folks, and see you on Friday.